more difficult than last year's.
That may be true too. Let's start on our next topic. And the next few topics, hash functions, authentication, digital signatures. We're not so much about encrypting data for confidentiality, we're concerned now about authentication. Making sure that the messages we receive are from the right people, have not been modified. So the services of authentication, data integrity, as opposed to the service of confidentiality. So let's explain first what a hash function is and how we use hash functions in cryptography and for authentication. And the next topic also covers authentication. So there's a close relationship. You've covered hash functions in some other course. What course?
In data structure.
Probably an introductory computer science, data structures and algorithms course. The concept of a hash function. Quite simply, some hash function h, we take some variable length input, m, and return a fixed size hash value of that input, m. So that we have some function h that takes some input, and that input can be of different sizes. And the output of that function should be a fixed size value, usually a small value for practical purposes. And importantly, this function, when we apply it to different input values, we should get different output values. And those output values, that is, if we apply to a large set of different input values, the output values should be evenly distributed about the space of possible values and should be random looking. That is, should the relationship between the output hash value and the input value there should not be some pattern, or should not be obvious as to what the relationship is. From a security point of view, we will use hash functions for authentication and similar services. What we need from such a hash function is that when we take some input value m and apply our hash function, it maps to our hash value, but given our hash value, it should be computationally difficult to find m, to go backwards. So we have a function we can calculate in one direction, but calculating in the inverse of that function should be computationally infeasible. We'll see why that property is required when we look at different applications to authentication. It's called the one-way property, a one-way hash function. Another important property that we'll need for security purposes is that if we take two different messages as input, m1 and m2, and apply our same hash function, that we get two different hash values in output. We don't get a collision. A collision would be if I apply my hash function on m1 and then I apply my hash function on a different message, m2, and get the same hash value out. That would be a collision. That will cause problems if we have such a collision, cause problems when we apply this for security purposes. So when we use a hash function for cryptography, we generally require these properties of one-way property and collision-free property. We will state those properties with a bit more detail later. I need some batteries. Okay. We're going to use the hash function to determine whether data has changed for the purpose of providing authentication and data integrity. And hash functions are used to authenticate messages. We receive a message. We want to make sure that the person who sent it is the right person. Digital signatures. We send a message, and to be able to prove that that message came from a particular user, that is, that sender signs the message in a digital form, we'll use hash functions there. We can use them in storage of passwords. That is, when you supply a password to a system, that password is initially stored in some file. When you log into a system, you supply your username and password. The system compares your supplied username and password to that stored in a file. If they match, you're allowed access. If they don't match, you're not allowed access. The storage of the passwords in the file will often use a hash function to provide some security mechanisms so that other people cannot access those passwords. Intrusion and virus detection. Although we're not going to cover in much detail this topic, maybe towards the end we'll talk about viruses, but the detection of intruders into a system or a virus on a computer can make use of hash functions as well, because they are effectively looking at signatures. We'll see how they work, especially the signatures, and how that relates to the detection of viruses and intrusions. So hash functions are used in different parts of security, computer and network security. This is a way to visualize what a hash function does. Hash function H takes some input, produces some output. The input is some message or some block of data, M. It may be variable length. Maybe it's 1,000 bits. The next time I apply that hash function, it's 10,000 bits. So I use the same hash function. I have different lengths input. I may need to pad that message to make it, say, an even number of blocks in length. Let's say my hash function takes messages which are a function or an integer multiple of 1,000 bits. That is 1,000 bits, 2,000 bits, 3,000 bits. Then if I supply a message which is 900 bits, I would need to pad that out to 1,000 bits. But still, so that's what this L is indicating. We apply some hash function and we get some hash value out. And that hash value, importantly, is fixed length and for practical purposes is normally small. Our message may be 10 megabytes or 1 gigabyte. The hash value would be a fixed length value, usually in the order of hundreds of bits. How can we use a hash function? If we want to verify the integrity of some message that has been sent, that is, the source creates a message, sends it across the network, the receiver receives that message, they want to make sure that a message has not changed. So that is the service of data integrity. Or make sure that the sender of that message is who they say they are. So this is verifying the integrity of the contents and authenticating the source user. A hash function is used to provide message authentication, these two services, by what's called a message digest. We take a digest of the message and send that along with the message. Let's see some examples of how it's used. The first example, we have a source and a destination, and we're sending a message, M. We want to provide these services of authentication at the receiver. When the receiver receives the message, they want to be able to check that nothing's gone wrong, nothing's been modified, and the source is who they say they are. In this example, we take the message, apply our hash function on that message. So this line we would have the message, this would have a hash of the message, which would be a small fixed size hash value. This operator is concatenation. We concatenate those two values. If our message was 1 megabyte and the hash of the message was 100 bits, we combine that 1 megabyte and 100 bits together. So we have 1 megabyte plus 100 bits, concatenate the two, and we take that and encrypt using symmetric key encryption in this case, just in this example. We'll see some different examples in the following slides. So the source A now encrypts the combination of the hash and the message using their secret key K, and they send that is the ciphertext, across the network. The receiver receives, decrypts with their secret key K, which should be the same as what the source had, and then does the verification. When they decrypt, they have the two values, the message and the hash value. So shown here, the white box, M, is the message. The grey box is the hash value of that message. And then they do the check by taking the hash of the received message and comparing that with the hash value received. That's the process. Let's see how that works in terms of what happens if a malicious user tries to modify the message along the way, and how this verification process can detect such modifications. So I'm going to not draw this part, but from this point on, we've sent a message, and we can write this message as it's the message concatenated with a hash value encrypted with a secret key K. So that's the ciphertext. And our malicious user receives that. They intercept the message. It's sent across some network, public network. The malicious user receives that. What does the malicious user know? They know the algorithms used, the encryption algorithm. They don't know the secret key K. That's secret amongst the source A and the destination B. The malicious user wants to, let's say, change the message. Change the message, forward it on to B to make B think that the message was sent from A and has not been modified. Let's see what the malicious user can do. Malicious user has the ciphertext that they've received. And the ciphertext is simply the message concatenated with a hash value encrypted with key K. What can the malicious user do? Or what can they try to do? They want to change the message. The ciphertext, let's think of it as a sequence of bits. Let's say they do change those bits. So let's put some numbers. Just as an example, our original message was 10,000 bits, and when we took the hash of that, so M is 10,000 bits in length. When we took a hash, the hash value was 100 bits. So in fact, what has been sent across the network is 10,100 bits, because it's just a concatenation. That is, at this point, after the concatenation, we have 10,100 bits. We encrypt that, and how long is the ciphertext? 10,100 bits. We're assuming we've got the right block size. So the ciphertext is the same length as the plaintext. So the length of C, 10,100 bits, where now let's change some of those bits. Let's say we change a sequence of bits at the malicious user. Which bits? Let's say they try to change any bits. Let's see if they change anything, see what happens. They can only change the ciphertext in this case. They cannot see the message. It's encrypted with a secret key, okay? If they change the bits in the ciphertext and send that on, what happens? When we decrypt with a secret key, what happens? B receives this change message. What's going to happen now?
It's the wrong message.
It's the wrong message.
Deals with a different hash value.
It's the wrong message. That is, if we decrypt and we get some sequence of 10,100 bits, let's denote it as, so we decrypt with a secret key K and we get, let's say, M prime, some modified message, and some received hash value. Instead of M prime, let's call it M1, hash 2. After decrypting, we have the message, which is 10,000 bits, and the hash value, which is 100 bits. If we decrypt, because the ciphertext has been modified, now we do the check at the receiver. At this point, we take the hash of the message, the first 10,000 bits, and compare it to the hash value received. So the hash of the message, let's say, gives us the value hash 1. Compare H1, the calculated hash value, against H2. Are they the same? No. Because if M has changed, the hash value would have changed. In fact, it's even simpler than that, because most likely the hash value has changed as well, the received hash value. Because we decrypted the key, we decrypted ciphertext with a key, we'd get plain text which is completely different from the original plain text. If they don't match, then the receiver detects something's gone wrong. With authentication, we don't need to detect exactly what's gone wrong. All we want to do is make a decision. Has the data been received, been modified or not? Not which part of the data has been modified, just a decision modified or not. If it has, if we detect modification or some change, then that indicates some problem. In this case, we detect something's gone wrong if the hash values don't match. And the same with all our authentication examples. If the two values don't match, then that detects something's gone wrong. And we'd need to use some other approach to then try and fix that. We're not covering how that works. Do we need a hash value in this example? What if we didn't use this hash and just encrypted the message, sent the message, no hash value? Do we provide any authentication? No, just using symmetric key cryptography, we take a message, going back to the very basics of symmetric key cryptography, take a message, encrypt it with key K, send it, malicious user intercepts, modifies the ciphertext, sends it on to B, B decrypts with key K. Can B detect something's gone wrong? Why do you say that? Use a CRC.
We calculated the difference between we have some a little bit checksum or some.
You're on the right track, but there's no checksum. Just go back to very simple. There's a message,
Or bit parity bit.
ciphertext. You're on again on the right track, but there's no parity bit. There's no checksum. If we have a message, encrypt it with a key, send it. The malicious user modifies the ciphertext, sends it on to B. B decrypts with key K. What's B going to do? Or what's going to happen at B? They may or may not know. Why would they know?
Because if for example, if the person A and person B know that try to send some text message, for example, text should be readable, right? And we encrypt with some block cipher, and we decrypt it, and the cipher has been modified, and we decrypt the modified cipher. The result is going to be unreadable.
So if the message that we're communicating has some structure that the receiver expects to see, then they'll be able to detect if it's been modified. If we used a Caesar cipher, our plain text was Steve, and we encrypted with some K equal to 1, then our ciphertext W, is it? We apply our Caesar cipher, encrypt, we send the ciphertext. If the malicious user modifies this, let's say they change it to T, A, G, W, F, and send that modified message on, and then the receiver B decrypts using key K equal to 1, they'll get some non-English word at the output. Just using symmetric key cryptography, without using a hash function, if the message that we're sending has some structure, for example, it's some English text, then if we decrypt ciphertext which has been modified, that's the original ciphertext, this is the modified ciphertext. If we decrypt that with the same key, we will get plain text which we do not understand, that doesn't have the expected structure. It doesn't just have to be English text. If it's a JPEG image, for example, a JPEG image has a particular structure. The structure of the file, the encoding and the header structure of the file means that if we modify something and decrypt, then if we modify the ciphertext, then the decryption of that file will not produce the correct structure for the JPEG file. So in fact, with just symmetric key encryption, we can provide authentication in terms of checking if a message has been modified. We don't need, in fact, to even do this. But if the message didn't have structure that we could detect, or we didn't know what the structure was, that's when using the hash function becomes useful here, to confirm the structure. And the point that was made before is that, okay, add a CRC check or a parity bit check. That's effectively what our hash function is doing here. It's adding some extra information. You see, it adds it to the end, like a CRC error check code or parity bits. Add some extra information such that the receiver can confirm that nothing's been modified along the way. Yeah, we make no attempts to correct any errors. Our goal is to know, has the message been modified or not? Not what the modifications were, just whether it's been modified or not. Let's see another example of how we can authenticate. Here we take a message, encrypt, we take a hash of that message, encrypt the hash value with our secret key, send the message and the encrypted hash value across the network. What security services do we provide? Can the malicious user read the message? Why can the malicious user receive the message? It's not encrypted. Here's our message, our plain text. This is sending from A to B. We take the message, we take a hash of the message, encrypt the hash value with a secret key, concatenate the message with the encrypted hash value, send that across the network. The message itself is not encrypted. There's no confidentiality provided here. Sometimes we don't need confidentiality, but we want authentication. We send the message and the encrypted hash value across the network. Now the attacker can modify the message. Let's see what they do. This is what's sent across the network. The message concatenated with the encrypted hash value of that message. Malicious user intercepts, changes the message. The message is modified, and let's say the new one that they're going to send on is M prime. A modified message, a different message. Can the malicious user calculate the hash value of this modified message? Can the malicious user calculate the hash value? Yes? Malicious user knows the message, they change it. Let's say the message was, please decrease Steve's salary by 10,000 baht. I receive, intercept the message, and I change decrease to increase. Okay? So the new message, M prime, is please increase Steve's salary by 10,000 baht. I can do that because I can see the message. I can calculate the hash of that message. Let's call it H prime. I need to send this modified message onto user B. Here's the modified message. I concatenate the modified message with what? With the encryption of this hash value. Encrypt the hash value, H prime, or the H of M prime. Encrypt with what? The key K. Do I know the key K? I don't know the key K. I'm the malicious user. The key K is a secret shared between A and B. So the question is now, if I try this approach, what can I encrypt with? I cannot encrypt with key K because I don't know what key K is. It's a secret key. Let's say I encrypt with a different key, K of malicious user. If I do that, let's see what happens at the receiver B. B receives this, M prime concatenated with the encryption of the hash of M prime using key K of malicious. B receives this thinking it's coming from A. So what B does, takes M prime, the received message, and calculates the hash of the received message. They've received M prime, they calculate the hash of M prime, gives them the hash value H prime. They take the ciphertext here and decrypt with the shared secret key K. Decrypt all of this. Essentially decrypt the ciphertext with the secret key K. They get some value after they decrypt. Let's call it X. And now they compare this value X with the calculated hash value. Are they the same? If they are, the user B believes the message. If they're not, it doesn't trust the message. The question is, are they the same? They're not the same. Anyone else want to try? Why are they not the same?
Because the key is used to encrypt is not the same as the key that is used for encryption.
Okay. We're using different keys. Remember, we're using symmetric key encryption here. E and D are just symmetric key ciphers. DES, triple DES, AES, Caesar cipher, whatever we choose. The ciphertext, that is this portion, was encrypted using K malicious, or the key of the malicious user. We decrypt that using a different key, the secret key shared between A and B. If we encrypt some ciphertext with one key and decrypt it with a different key, we will not get the original plaintext back. So we will not get the plaintext. The plaintext was the hash of M prime or H prime. We will not get that because we decrypted with the wrong key, essentially, since these two keys are different. Therefore, the value X will not equal H prime, and therefore we've detected something's gone wrong. So in that example, the malicious user intercepted the message, modified the message, recalculated the hash value, encrypted the hash value with a new key, the key that the malicious user knows, and sent all of that on to B. B received the modified message, received the encrypted value, decrypted the encrypted value with their own key, K, compare those values, and finds that they don't match, and therefore finds that something's gone wrong in this data delivery and doesn't trust the data that's been received. That is, authentication has been successful. I know some of you are very malicious. What else can you do if you want to defeat this system? Can you try something else? I don't know how you would meet in the middle. Let's go back. So the problem there, the malicious user doesn't have key K, the shared secret key. Therefore, they can only try some other key. And because we know if we encrypt plain text with one key and decrypt it with a different key, we will not get the original plain text back, then the authentication works. Try something else. Malicious user receives the message, modifies the message to M prime. They take this portion and do not modify it. They send it as is. That is, we send E, or the encryption, using key K of H of M. Remember, the message, for example, is 10,000 bits in length, plus another 100 bits at the end. So what the malicious user has done is modify the message, change the first 10,000 bits into something that they want it to be, but the last 100 bits, they've just taken a copy of them. The ciphertext, which is the encryption of the hash value, they've just taken a copy of that exact 100 bits and send it on to B. B does the check again. B has the receive message, M prime, calculate the hash. The hash of M prime equals H prime. They have the received ciphertext value here. They decrypt that. Decrypt using key K of the hash value of M encrypted using key K. That is this value decrypted using key K. What's the answer? H of M was encrypted with the key of K. We decrypt it with the key of K. We get H of M, which is, let's say, H, the hash of M. Compare these two values. Are they the same? Are they the same? Are they the same? No. This value is the hash of M prime. This is the hash of M. M and M prime are different messages. M was decreased Steve's salary by 10,000 baht. M prime is increased Steve's salary by 10,000 baht. Our property of our cryptographic hash function, our desired property, is that if you apply the hash function on two different messages, you'll get two different hash values. Let's go back to remind what we want from our hash function. Collision-free property. Take the hash of M1, gives us one hash value. Take the hash of M2, should give us a different hash value. If we have that property, then it's a collision-free property, which is desirable. And that's what we need for this authentication to work, because the hash of M prime gives us one hash value. The hash of M gives us a different hash value. Now when B compares H prime to H, he finds they're different and now has recognised something's gone wrong. The thing that went wrong is that malicious user changed M to M prime without changing the encrypted hash value. So again, malicious user modified something, in this case just the message. B detected that modification and therefore successful from B's perspective. So two cases in that example. Malicious user tried to modify the message and calculate a new hash value. That was unsuccessful because the malicious user didn't know the secret key K. The second approach, modify the message and reuse the old encrypted hash value. That was unsuccessful because of the collision-free property of our hash function. The hash of two different messages should be different hash values. What else can the attacker do? Anything? That's the main things. They would need to know the secret key. Or, if our hash function didn't have that collision-free property, if the malicious user could find some message M prime which had the same hash value as the original message M, our malicious user would be successful in that case. If M and M prime are different, but their hash values are the same, then what would happen in this case, malicious user modified the message, B would decrypt, find H, compare it to H prime. If they're the same, B would believe that nothing's gone wrong. So an attack on this authentication system would be successful if the malicious user can find a message that has the same hash value as the original message. So we need a hash function that it's very hard to find such message. We'll return to those properties and analyse them in some more depth soon. How does this compare to the previous example? Provides authentication. It doesn't provide confidentiality. Sometimes we want to send a message. We don't care if someone else sees the message, but we care if it's been modified, if we cannot confirm who it came from. This does that. Note that this approach, we encrypt only the hash value. In our example, the message was 10,000 bits, the hash value was 100 bits. Encryption takes time. Encrypting a message of 10,000 bits is going to take 100 times longer than encrypting a message of 100 bits. If our message was 10 megabytes, our hash value was 100 bits, encrypting the entire message can be very time consuming, whereas encrypting just the hash value can be quite fast. So this approach has the advantage in that we don't encrypt the entire message, we just encrypt the hash value of the message, a small representation of the message, a performance advantage. Do you have any more examples? Here's one. So the previous example showed the requirement for collision-free property. Hash function of two different messages should give two different hash values. We don't want collisions. Here's a different example. The goal, or the scenario is that both A, the sender, has some secret S, and B, the receiver, also knows that secret S. They want to confirm that when B receives a message, it wants to confirm that the message came from A. How do they confirm? If that message has that secret value, and only A and B know that secret value, then B will know it came from A. That is, if the message contains the secret, when B receives that message, if it contains the secret, it must have came from A, because the only other person in the world that has the secret is A. That's the idea here, checking who it came from. How does it work? Let's not do this one. Let's do a simpler one and see the goal. The goal is that A wants to send a message to B, message M, and when B receives it, B wants to make sure it came from A. One way to do that, both A and B have a secret, S. A sends the message as well as the secret to B. When B receives this message, because it contains the secret S, it matches this secret value, therefore it must have came from A. So this is authenticating the source in this case. Why doesn't this approach work? Very simple example. A takes the message, concatenates the secret, sends that to B. B confirms the identity of the sender by comparing the received secret with their known secret. Even simpler, you're correct. What's the problem? You're correct, but there's an even simpler problem with this approach. Attacker knows the secret. Okay, it's not secret. If we send the secret in the message unencrypted, then the attacker just knows the secret and they can do whatever they like. They can pretend to be A from now on and send messages with the secret. So of course this will not work. So what we do to achieve the same goal is take a hash of the secret and the message combined. Let's see how that works. A has a message they want to send to B and the secret value that is known. They combine the message and the secret. So here's the concatenation operation. Get some hash value and take the hash of that combination of the message and the secret. They calculate some hash value and they send across the network the message that they want B to receive concatenated with this hash value, H. B receives this, B has the message, and B now checks whether it came from A. How do they check? They take the known secret, B knows the secret S, concatenated with the received message M, so that B receives a message M, they know the secret already, it's shared between A and B. They take the received message, concatenate with the known secret, take the hash value, get some hash value, let's call it H prime, and compare that to the received hash value. Do they match? Does H prime equal H?
Yes.
Yes. We look at how they were calculated. H, the initial hash value which was sent, this H, is calculated by M concatenated with S. H prime is calculated from M concatenated with S. If we take the hash of the same value 2 times, we must get the same hash value as output. So this confirms that B, from B's perspective, that A sent the message. The message is not encrypted. We're not trying for confidentiality here. We're just trying to authenticate the sender. B wants to know that this came from A, not someone pretending to be A. How do we attack this? What does the malicious user try? You're malicious today. What are you going to try? Well, let's start simple. Let's try and modify the message, just to see that it works. Malicious user intercepts M concatenated with H. If the malicious user, say, modifies the message and sends it, sends M prime, can the malicious user calculate H prime, where H prime, so M prime is the modified message, H prime is the hash of the modified message concatenated with what? Malicious user doesn't know the secret, so they cannot do this approach. They cannot modify the message and try to calculate the correct hash value, because to do that they need the modified message and the secret value. But they don't know the secret value, it's secret. If they use something different, if they use S prime, some different value, then send this to B, B does the check. Hash of the received message, M prime, concatenated with S, let's say equals x, does x equal h prime? Does x equal h prime? No. X is the hash of m prime concatenated with s. H prime is the concatenation, or is the hash of the concatenation of m prime and s prime. S prime and s are different because the malicious user doesn't know the shared secret s. So that's unsuccessful because we would detect this received hash value and the calculated hash value are different. Something's gone wrong. Anything else we can do? If we don't calculate this and send the original h, send m prime concatenated with the h that was received, again it'll be unsuccessful because the hash of m prime and the secret equals some value. It does not equal h, which is the hash of m and some secret. So again, the malicious user will be unsuccessful. The attack will be detected if that is attempted. What else can the malicious user do? Can they find the secret? Or how do they find the secret in this case? You use the wrench, the hammer on the person's head and say, if you don't tell me the secret, I'll hit you on the head. Unfortunately, you cannot try that in the exam. Let's look what they would need to calculate to find the secret. They know, the malicious user knows m. M is not confidential. There's no attempt to keep m secret here. It's just sent in the clear. They know the hash value. The hash value is, and they know the hash function. The hash function is secret, it's public. Sorry, it's not secret. The hash function is public. So, malicious user knows h, they know m, they know the function. They need to find s. Because if they find the secret, the system can be defeated. How do they find s? Here we have a function, h equals the hash of something, where that something is m concatenated with s. If they can do the inverse of the hash function, they know h, lowercase h, they know the hash value. If they know the inverse function, then they can take lowercase h and apply the inverse and they'll get m concatenated with s. And if they have m concatenated with s, m is the first 10,000 bits, s is the next set of bits. They know m, they can easily find out what s is. If you have m concatenated with s and you have m, then you easily know what s is. So what the attacker needs to do is, given the hash value, find the original message, the input to the hash function. Now here's our property, or our desired property of our hash function. If that's possible, our system will be defeated. If we go back, one of our desired properties of our hash function is the one-way property. We can take the hash of a message and get the hash value, but we cannot go back the other direction. Given the hash value, find the message. That is, it's easy to calculate the hash of some message and get the hash value, but it should be computationally hard to, given the hash value, find the original message. This one-way property, if it holds, then the example system we've gone through is successful. It's secure. If it doesn't hold, then the attacker can find the secret and the system is not secure. So we need our hash function to have this one-way property if we want to use such an authentication system. So we've seen these two properties and see why they're needed. One-way property is needed in this case so that the attacker cannot discover what S was. The collision-free property is needed so that the authentication can work. That is, the attacker cannot modify the message and get a hash value of that modified message which is the same as the hash value of the original message. We do not want collisions to be able to occur. If they can, the attacker can defeat the system. Note that this example message authentication protocol didn't use any encryption. Again, that can be beneficial. Encryption is slow in some cases. Sometimes if you need to use particular algorithms, they need licenses, they're costly. So avoiding encryption to perform authentication is of benefit in some cases. That's why this system or this authentication example is valuable. So there's three examples of how we can apply hash functions to provide authentication. There are other variations which we'll see in subsequent slides. What's this one? This essentially combines some of the previous approaches. It combines shared secret or symmetric key cryptography, similar to the first approach, and the secret, similar to the previous approach. So it's a combination. And we can have other combinations as well. And you can see, and you can do this analysis, what can the attacker attempt to do, and then see how does B detect the modifications. Authentication and encryption go together in that with encryption only, we can provide some authentication. We said in our example with our Caesar cipher, if I encrypt some plain text with some key, if the attacker modifies the ciphertext, the receiver will be able to detect that because it doesn't decrypt successfully. So we can provide authentication using just symmetric key encryption. But sometimes we want to avoid encryption. If we want to provide the service of authentication, we want to avoid doing encryption. Why? Encryption can be slow. You have a large message, if you need to encrypt it, that takes time. It has some costs. If you want to encrypt in hardware, then you need to pay for hardware that can do that. So there's some financial costs involved in performing encryption. If we have a small piece of data, some hardware encryption algorithms can be also inefficient or slow. Encryption algorithms, sometimes you need licenses to use them. They are patented, and therefore, again, there's some cost incurred of using them. So sometimes we don't want to use encryption if we don't need it. And we saw an example before that provided authentication without relying on encryption. Another approach for authentication without using encryption algorithms is what's called message authentication codes, a MAC. And similar to hash functions, except we have a key. Our hash function takes some input and produces a hash value. A MAC function, a message authentication code function, takes some input as well as a key and produces some MAC code similar to our hash value as an output. And we can use it in a similar way to provide authentication. The next topic covers MAC functions in more detail. There's similarities to hash functions. We'll cover that shortly. Let's use symmetric key encryption to provide authentication. If I encrypt some message with a symmetric key encryption, I know the secret key, the destination knows the secret key. If I encrypt the message and send the ciphertext, then we know that we have some form of authentication, because if the destination can decrypt successfully, then it must have been encrypted with a secret key. Who encrypted that message? You receive a message, it successfully decrypts with a, let's have an example. You have shared a secret key with another user. You've received a message, it successfully decrypts with the secret key. Therefore, who sent that message to you? The person who has that secret key. So that's how authentication is provided with shared secret key encryption. If you receive a message and it successfully decrypts with a secret key K, which is shared with some other user, then some other user must have sent that message, authentication. If someone else sent the message, then they wouldn't have the shared secret key. Let's say, same situation. You have some message which is encrypted with a secret key, K, which you've shared with the other user, and you want to confirm to me, the third party, the lecturer in the class, you want to confirm that that message you have came from this user. Can you do that? Can you convince me that the message that you have came from this other user? Can you convince someone else that the message that you have came from this other user? Can you convince me that it didn't come from this user? If it came from some third user, then it wouldn't decrypt successfully. So I can be convinced it didn't come from some other user. What about convincing me that the message came from user A and it's not some message that you created on your own? That's impossible. That is, we can be sure that that message was encrypted by one of two people in the world. One of the two people who have that secret key. So the message was either encrypted by user A or user B. But we cannot be sure which user encrypted the message. Some services, we want to be sure that a particular message came from just one user in the world, a signature. With symmetric key encryption, we can provide authentication, but we cannot provide the concept of a digital signature. Because with symmetric key encryption, the key indicates that one of two users has encrypted that message. A digital signature is confirming that some message came from one particular user in the world. So to provide a digital signature, we use public key cryptography, asymmetric key cryptography. That is, we encrypt with a private key of a particular user, meaning we can only decrypt with the corresponding public key. And we'll see how we use hash values here. Hash functions. You receive some ciphertext. You receive an email on the email list. and it contains the value of C. What do you know? You receive an email containing the value C, where C is calculated from encrypting some message M with a private key of me. Do you know the message?
Yes. No message, no.
We've got two answers, yes and no. Let's get a third one to confirm. You know the ciphertext C, it's encrypted, it's some message M encrypted with my private key. Do you know the message, or can you find the message? We've got more people saying yes. Why? Because you can decrypt with a public key. You know C. You can decrypt with the public key of Steve, C, and that gives you M. So if you know C, you can find the message. What else do you know if you know C? What can you confirm?
It comes from Steve.
You can confirm that it came from me and no one else in the world, because only I have my private key. If C successfully decrypts with the public key of Steve, then it means it must have been encrypted with the private key of Steve, and there's only one person in the world that has the private key of Steve, therefore the message came from Steve in this case. So this is the concept of a signature. We now have a message, and the receiver of this message can confirm where it came from. The particular user in the system, only one user in the system. And that's the basics of a digital signature, except in a digital signature, to keep things more efficient, we normally take a hash of the encrypted message. We see here we have a message. We take a hash of the message, encrypt the hash value with a private key of user A, concatenate the message and the encrypted hash value, send it. The result is that the receiver B, they know the message, and they can confirm that that message came from user A because they decrypt with the public key of A, the encrypted hash value, and they get the hash value and compare it to the hash value of the received message. If they match, everything's okay. So this is what user A sends, the message concatenated with the hash of that message encrypted with a private key of A. Only user A knows this private key. Malicious user intercepts. What can they do? Can the malicious user see the message? Yes, the message is not encrypted. We don't have confidentiality here. The message is here. There's no attempt to hide the message. Let's try and modify the message. Malicious user modifies the message to M prime, and they concatenate. What can they try? Let's try both approaches. Since we've modified the message, let's take the hash of that modified message, hash of M prime, and encrypt that with what? What does the malicious user encrypt with? We don't know the private key of A here. So we need to encrypt with some other private key of the malicious user. And you know now, when B receives this, they'll try to detect if there's any modification. They'll try and decrypt this with the public key of A. Because the message says it came from A, therefore it should decrypt with the public key of A, but it was encrypted with the private key of the malicious user, therefore it will not, well, it will decrypt, but it will give us the wrong value when we compare the hash values. So we have the wrong key here, so we cannot encrypt the new hash value. That will be unsuccessful. What else can we do? We can do this. We receive the message concatenated with this signature. This is the signature of the message. It's the hash of the message encrypted with the private key of the sender, the source. Take this value. It's a sequence of, say, 100 bits. We don't know what the private key is, but we can still copy that sequence of bits. So we take the modified message, copy the sequence of bits representing the signature, and send that on to B. What's going to happen at B? B, the hash value will be different, because if we send this on to B, B calculates the hash of the received message, H of M prime, and compares it after decrypting this. They decrypt with the private key of A, sorry, the public key of A. Let's call all of this C. They decrypt this with a public key of A because the message says it came from A. The answer will be H of M. Compare H of M with H of M prime. If our collision-free property holds for our hash function, they'll be different. And therefore we detect something's gone wrong. So again, the attacker is unsuccessful here. Anything else the attacker can do? Try to modify the message without modifying the signature. That will be detected. Try and modify the message and create a new signature because we don't have the private key of A. That will be detected. Anything else? Man in the middle attack, not meet in the middle that we covered before the midterm about triple death and double death, but a man in the middle attack could be attempted. We'll see that in some detail shortly. What else could we do? When B receives the message, they try to perform the check. And how they perform the check is they say, okay, this message came from A, therefore I decrypt the signature using the public key of A. So let's say that the message came from me. You receive this message, you're B. The message you think came from Steve, therefore you'll decrypt using the public key of Steve. But what happens if a malicious user has intercepted, modified the message, calculated the hash of the modified, and encrypted using the private key of the malicious user, and also the malicious user has convinced you that the public key of Steve is not in fact Steve's public key, but is the public key of the malicious user. That is, if you think that this public key is my public key, but it's in fact the public key of the malicious user, then you will not be able to detect this attack. So this authentication relies on that if you have the public key of user A, that it is indeed the public key of user A and not the public key of someone else. In practice, it's possible to perform an attack such that, okay, I post on my website my public key. All of you go, and therefore you know my public key. But some malicious user somehow gets access to my website and changes the public key. So you now think it's the public key of Steve, but it's in fact the public key of the malicious user. So when I send you a message, the malicious user can modify that using their private key and convince you that it came from Steve when in fact it didn't, or it was modified. So this relies on the recipient user knowing the correct public key. And there's a potential meet in the middle attack, which is related to that. Man in the middle attack, sorry. So there are some assumptions that we've made here, that the public and private key pairs have been successfully and securely distributed. If you have the public key of A, it is the public key of A, not someone else. Figure A in this digital signature, we call the encrypted hash value the signature. So in this, we have M concatenated with the signature, the signed message. So we sign a message by taking the hash of the message and encrypting with the private key of the user. Why not just encrypt the message? Why do we need a hash value here? Why not just take M, encrypt with the private key of A of M? I think you'd also find if you encrypt with the private key of A that if the message is modified, that you'll be able to detect that if the message has some structure. The main reason is for performance. M is a 10 megabyte file. I want to sign it. If I don't take the hash value and simply encrypt the message with the private key of the user, then the ciphertext is also, the signature is also 10 megabytes. So I have to send 20 megabytes across the network. A, encrypting takes a lot of time, encrypting a 10 megabyte file, and B, sending 20 megabytes across the network just to send a 10 megabyte message is inefficient. So the approach is we take our message, take the hash of that message, and our hash function takes a variable size input and produces a fixed, normally small sized output. Let's say it's 256 bits, the hash value, and encrypt the hash value, like we do here, encrypt the hash value with a private key of A. So the signature now is just 256 bits. I send the message plus the 256-bit signature across the network. Advantages: the encryption is much faster. I'm only encrypting a 256-bit value as opposed to a 10 megabyte plain text. And the network overhead is much less. I'm only sending an extra 256 bits across the network as opposed to the full 10 megabytes across the network. So the real advantage of encrypting the hash value as opposed to encrypting the message is performance. So in most practical cases, the signature is considered the encryption using a private key of a user of a hash value as opposed to of the message. But we could achieve the same security goals by just encrypting the message. Diagram, the figure B on this slide, what does it do? It combines the previous approach, but it also encrypts everything with symmetric key encryption. That is, take the message, calculate the hash value of the message, encrypt with a private key of A, concatenate with the message, which is all the same as this part in figure A, but now, instead of sending the message unencrypted, encrypt everything with a symmetric key cipher using a shared secret key K. In this case, we provide confidentiality as well as authentication. The attacker cannot see the message in this case. And we can still authenticate using the signature.
Can we encrypt with the public key of the
Or we could use public key cryptography here. In this example, figure B, we use symmetric key cryptography to provide confidentiality. We could have used public key cryptography to provide confidentiality. So, a digital signature is provided using public key cryptography, where you use the private key of the source to sign the message. For performance reasons, normally the signature is taken of the hash of the message, not the entire message. That keeps it short. We cannot use symmetric key cryptography for a digital signature because with symmetric key cryptography, two people have the shared secret key. So if you sign the message with your shared secret key and I have that message, the signed message, I cannot confirm whether it came from you or the other person that you shared that secret key with. It could have come from one of two people in the world, but that's not good enough in some applications. I want to know that it came from one particular person in the world. And that's the main benefit and a main practical benefit of public key cryptography. There are different hash functions available. I'll show you some on the computer in a moment. A very simple one, algorithm, is using an XOR on the bits of the message. Just to demonstrate something we can calculate on the board. We have some message. In this example, it's 12 bits long. We'll apply this algorithm to calculate the hash value of this message. The algorithm states that we calculate the hash code by dividing the message into blocks. So into n-bit blocks. Let's say in our example n equals 3. How many blocks do we have? Three-bit blocks. Have I missed something? We have 4 blocks. Just for this example, let's say we have some message we want to calculate the hash of. We have 3-bit blocks, n equals 3. Therefore, we have a 12-bit message and therefore 4 blocks. Bij is the ith bit in the jth block. Say I equal to 1. C1 equals B11. If I equals 1, look at this equation, then C1 equals B11 XOR with B12 XOR up to B14. Where B11 is the first bit in the first block. B12 is the first bit in the second block. B13 is the first bit in the third block. Block 1, 2, 3, 4. B11 is the first bit in the first block equals 0. XOR with B12, which is the first bit in the second block, which is 1. Here's the second block, here's the first bit. B13, third block, first bit. Fourth block, first bit is 0. What do you get?
0.
I think so. Just XOR those 4 values, and that becomes the first bit of our hash code. We do it again. 0 XOR 1.
From left to right.
Yep. 0 XOR 1 is 1 XOR, so the answer is 1 XOR 1 is 0 XOR 0. So the answer is 0 here. We do that, I'll not do it, for C2. Where C2, we take the second bit of the first block, the second bit of the second block, the third block and the fourth block, XOR them. 1 XOR 1 is 0, XOR 0, 0, 0, we get 0. And then for C3, we take the third bits of each block. 0 and 1 is 1, 1 and 1 is 0, 0 and 1 is 1. Just take the first bit of each block, XOR them, then take the second bit of each block, XOR, and the third bit of each block. Our hash value is in fact C in this case, is C1, C2, C3. Sorry, 0, 0, 1. 0, 0, 1. Message 12 bits, hash value, hash code 3 bits in length. Just a very simple example of a hash algorithm. Easy to implement using XORs on the bits. If my message is 1000 bits in length, how long is the hash code?
1000 bits.
Message is 1000 bits. How long is our hash code in this example? Let's try simpler then. In this case, the message is 12 bits. If I added on 3 more bits, how long would the hash code be? 3. The hash code with a block of 3, 0, XOR 1, XOR 1, XOR 0, XOR, we just XOR another bit, would get a value of C1, C2 and C3. If our block length is 3 bits, our hash code will be 3 bits. If our message is 1000 bits with a block length of 3 bits, our hash code is still 3 bits. So here we get our fixed length hash code no matter what the length of the input message is. That's our required property of our hash function. If we want a longer hash code, then we just change the block size. Let's finish with an example of a real hash function or a used hash function. One practical hash functions are more complex than that. One example that you probably heard of is MD5. MD5 is a hash algorithm. It takes a variable size input and produces an output of how many bits? Anyone remember? 128 bits, I think MD5 is. Let's check anyway. MD5 is just another hash algorithm. Takes its input, produces a hash code as output. You'll see that on some cases when you download files. That is, to verify the integrity of the file that you download, then there may be a hash value provided. I've downloaded an Ubuntu install disk, okay, in the past, an ISO file. 733 megabytes, so it's an install disk or a CD for installing Ubuntu Linux. I want to confirm whether the file that I downloaded it from a mirror in Thailand. I want to confirm that the file I downloaded has not been modified in some way. Maybe some malicious user has modified the install disk such that when I install the operating system, there's some virus or some malicious code on my computer. And when I install it, everything looks fine. How would I know that there's nothing malicious in this 733 megabyte file? First, we can calculate the hash of this file. And most operating systems, Windows, Unix, have MD5 implemented where you can calculate the hash of some file. The name of the program here is called MD5 sum, where I just provide the file name and it goes away and it calculates of this 733 megabytes the hash value. It takes some time. There we go. Sorry, just so we can see it. Okay, the first character, if you cannot see it, is an 8 there. 8468, and so on. These are hexadecimal values. How many bits? 128 bits there. So each hexadecimal value is just a 4-bit value. So this is a 128-bit hash value of that file. So the 733 megabyte input produced a 128-bit output. Now, how do I check that that file has not been modified from the original source? Well, I need some way to confirm that that hash value matches the hash value of the original file. And in practice, what I'll do, I'll copy that. And so I'll copy the hash value and go to the website for the Ubuntu download. And on the Ubuntu official website, they list a set of hash values for those images that you download. Now, I trust this website because it's at the Ubuntu domain, so I need to trust it for this to work. So there's a list for different files that I could download, the hash values. I'll do a search for the one that I just calculated. It's found, luckily. You may not be able to read it, but down the bottom is the hash value that I just calculated and the file that matches the file that I downloaded. This confirms, if I trust this website, then this confirms that the file that I've downloaded matches the original file that was provided. Why do we know it matches? Because if the two files were different, that is the one I downloaded and the one that was originally made available, if they were different, they should produce different hash values. And I would detect that. So this confirms that they're the same and that I can trust it.
If we have two PDF files
Mm-hmm.
and we download from two different sources, and if we use this function to calculate the hash value and compare them, if they are the same, it means that they are from the same delete. Actually, they are from the same source.
So if you have two PDF files and you calculate, say, the MD5 hash of both of those files, if the hash values are the same, then you can be confident that the two files are the same. Did they come from the same source? Well, that's a different factor. If you want to know where it came from a particular source, then you need to, for example, in this case, get the original hash value that the source created and believe that that's their hash value. So in this case, I need to trust this website. If a malicious user could modify this website and put a different hash value here, and then modify the ISO CD image, the one that I download, to match the hash value here, then I would be tricked into thinking that the file I downloaded has not been modified. So it requires that you can trust the original source of the hash value. That is, I can trust this value. So the file I download, calculate the hash value, compare to the trusted hash value. If they're the same, I believe that the file I downloaded has not been modified. And yes, you can compare two files to see if they are the same. But there are other ways to compare files.
Normally when we do MD5 sum, we use only the data of the file, not including the metadata for example, file name.
Yes, in this case, it's just used the contents of the file. The 733 megabytes, it applies the algorithm. MD5 is more complex than this, but if we used our bit XOR algorithm, we just take all those bits and XOR according to a 128-bit block and get the hash value. Let's change the file name. Just change the file name. I think if you check, so all I did is I changed the file name to abc.txt and calculated the MD5 sum, applied the MD5 algorithm on that file, and you can check these values. I think you'll see that they're the same. The MD5 is calculated on the file contents, not on the file name. So what's in the file, not the name. Okay, let's change the file. I'll take my original file. I'll create another file which just has one word in it. All right, hello. Just a text file. There's extra.txt, and take my original. Where is it? Ah, sorry, ABC. So the file is now abc.txt, and I'll cat extra. I'll just concatenate two files, the original ISO image, which is now abc.txt, and this text file, which just has the word hello in it, and I'll put them together into this new file called the Ubuntu ISO file. Hopefully it's fast. And now calculate the MD5 sum on the new, this ISO file, which has the original CD image plus this extra.txt. It's different. Compare these digits to these or these digits, and completely different there. And the idea of a good hash algorithm is that the hash values will be random looking hash values. So changing the input message by 1 bit should change the output hash value by many bits, like the avalanche effect. And we've seen that, all right, we changed it by 5 bytes, but very similar.
What's the advantage of CSC322 compared to MD5?
A CRC check has a similar concept, a error detecting code, but an error detecting code is detecting errors in a particular file. So it's the algorithms are just different in terms of the implementation. So there may be difference in terms of performance of the implementation. So for security purposes, we need to have these properties like one-way property, the collision-free property. Whether a CRC check has those properties as strong as MD5, I'm not sure. I don't think so. I don't know. But same concept. There are other algorithms, and the main other one in use today is called SHA, S-H-A. We'll see some examples of that, and we'll mention the concepts of these algorithms in some later slides. Any last questions on MD5? Just a quick demonstration of it being used in practice, not an explanation of how MD5 works. That's too complex for the time that we have.